Hi, here we will talk about a very important concept in studying momentum, the concept of collisions. So we often hear about collisions between cars and objects in our daily life. Now it's time to look at the physics behind it. Previously we have learned that momentum initial plus the impulse net equal to the final momentum. The impulse is provided by a net force, net external force acting on a system of objects. However, when you don't have any net external forces, it is legal to set the net impulse to zero. In what kind of systems can we find that situation? In isolated systems. And in collisions or explosions, we often end up with isolated systems. How? During a collision, the collision forces between two objects, for example, when two cars collide, the collision forces are often very much higher than any other external force like friction that may be involved. So we can approximate such kinds of scenarios as being isolated events, and we call these systems of colliding objects as isolated systems. When it is legal to consider isolated systems, such as in collisions or explosions, when something explodes, the explosion force is often very much greater than any other external forces present, then we can set the net impulse by any external forces to zero. What is the consequence of doing that? If we set I net to zero, we have the initial momentum is equal to the final momentum during a collision. So what does this mean? This means a conservation law. So momentum is conserved, that is, it is same as it was before the collision and it is the same as after the collision, saying that momentum is conserved in any collision. All right. So when can we not set this net impulse to zero? When a system can be directly impacted by external forces like gravity or air resistance. For example, take a basketball dropping on the floor. So when the basketball collides with the floor, the collision force is not as big enough to let us be able to ignore gravity. So if we don't ignore gravity, then that is not an isolated system. Hence, in that position, it's not, in that scenario, it's not legal to set the net impulse to zero, and we don't have momentum conservation. Some momentum is lost due to the net gravity or net force providing an impulse on the system. All right. However, in many situations, we will approximate our problem such that we have isolated systems, and we can go ahead by using our momentum conservation law. And whenever in any problem you see a collision taking place or an explosion happening, first thing or first instinct should be, can I try momentum to solve this problem? Because whenever there is a collision, momentum is involved. Okay, there are two types of collisions, and this is a link between collisions and momentum and energy. How? We define elastic collision to be collisions where the kinetic energy is conserved. That is, the final kinetic energy of an object is equal, of a system actually, is equal to the initial kinetic energy of the system. And similarly, we define inelastic collisions to be collisions in where the initial kinetic energy of the system is not the same as the final kinetic energy of the system. But remember that in any collision in an isolated system, momentum is always conserved regardless of kinetic energy. An example of elastic collision would be the collision taking place between two billiard balls on a billiard table with very negligible friction. In those cases, momentum and energy are both conserved, so that no energy is being lost to friction or any other forms. All right. An inelastic collision would be a collision when you have two things sticking to each other, or two things that loses some kinetic energy in the process. All right. And let's examine some examples regarding both of these types of collisions. In this first example, we have, let's say, two football players. One is running towards the other. So M1 is player 1 who's running towards a player 2, which is M2, whose masses we know. M1 has a mass of 85 kilograms, M2 has a mass of 105 kilograms, and M1 was running towards M2. m1 with a speed of 7 meters per second while m2 was at rest. After the collision, we want to know what the speed of m1 and m2 is. So what happens during, say, a tackle between two football players? One tackles the other, and just after collision they move together. So in this scenario, after collision, we are considering both of these players to be together for a short period of time, and we want to find what that speed is. All right. Now, why is it okay for us to use momentum conservation here in collision? Like on a football field between two players, there is friction, there is gravity, there are all sorts of these external forces. However, if you would remember, impulse is defined as, the net impulse is defined as the net external force times the time for which that force acts on the object, delta t. But a collision lasts very short time. For collision, del t is very small. If del t is very small, then this product is very small, and we can effectively set the impulse to 0. That is why it is legal to use momentum conservation in collisions like these. All right, so let's begin. So momentum is always conserved in any collision. So we start with that. Pi is equal to Pf, as simple as that. Now, before we start writing down equations, let's draw a simple diagram. That's what we do for any physics problem. So let's call one part of the diagram before, meaning whatever was happening in the system before collision, and another part, let's call it after, meaning whatever was happening after collision in the system. What is this system? This system consists of two players and nothing else, m1 and m2. So let's, since we are dealing with vectors, we want to specify a direction. Let's consider plus x in the rightward direction to be positive. All right. So we have m1 running towards m2. m2 was at rest. So we say that v1 I, that is the initial velocity of the first player, is equal to 7 meters per second. The initial velocity of the second player, v2I, was 0 meters per second. This was all that was happening before collision. Nothing else was happening. No external forces, nothing. All right. After the collision, they collide and then they move together. So we have these two players, m1, m2, now moving towards the right together. Why they are moving to the right? Because m2 was initially at rest, m1's momentum was to the right. So when m1 collides with m2, the momentum carries both of them to the right. And we want to know what this V final is, Vf. That is our target. We will use Pi is equal to Pf. Now, what was momentum? Definition of momentum was P equals mass times the velocity. Let's work with this equation then. For Pi, we will have how many objects we have in the system? 2. So we have the summation of m1 times v1 and m2 times v2. That is equal to, in the final situation afterwards, we have m1 and m2 joined together into one object. So we have one velocity. m1 plus m2 is now one complete mass with one common velocity, Vf, that we are looking for. All right. V2, let's also give these i's, and that is f. So i's on one side means initial and f's on the other side means final. So V2I was 0, so this term goes to 0. What are we left with? We are left with m1 times v1i. m1 is 85 kilograms times v1i is v1 is 7 meters per second to the right, so it's positive. 7 plus 0 equal to m1 plus m2, 85 plus 105 times vf. Divide both sides by 85 plus 105 to get vf. So we have 85 times 7 over 105 plus 85. That will give me what vf is. Therefore, vf is equal to 3.13 meters per second. And the sign is positive, meaning that it indeed both of them were moving to the right. If the sign came out negative, then I would know that I should have flipped the direction. No matter, if you follow through the process and trust in your choice of axis and be consistent with your signs, you will always end up with the right answer. So what does this mean? This means that both of these players were moving with a velocity of 3.13. Since both of these players were moving together, they both have the same velocity after collision. These kinds of situations, when two objects stick together after they have collided and move with a common velocity, is known as a perfectly inelastic collision. All right. However, in the real world, most collisions are not perfectly inelastic. They are inelastic collisions, meaning that inelastic collision only has momentum conservation and no energy or kinetic energy conservation. Perfectly inelastic collision means that both of them, their initial kinetic energy was not equal to the final kinetic energy. Kinetic energy was not conserved, but both of them also moved together with the same velocity in the aftermath of the collision. All right. So this is an example of a perfectly inelastic collision. All right, let's examine this example where a 4 kilogram block moving to the right collides elastically with a 2 kilogram block initially at rest. 4 kilogram block had a speed of 6 meters per second. We want to find their final velocities. The key word here in this question is elastically, meaning these two blocks collide in an elastic collision. So in an elastic collision, we know that kinetic energy is conserved. And how will this look if you were just looking at a situation and trying to determine if the collision taking place were elastic or inelastic? Well, elastic collisions would generally look like one object will hit another object and then maybe they will bounce off each other, or one will stop, the other will move, depending on how much energy transfer actually took place and how the energy was distributed between the two objects, all right, in the system. So a perfect way to examine your knowledge of inelastic or elastic collisions would be to try out playing pool, because in a billiard table the collisions taking place are nearly always elastic if you're taking your shots right. All right. Okay, so let's start with a diagram of the situation as always. Before, after, choosing rightward to be my positive x-axis. Before, we had the 4 kilogram block moving to the right at an initial speed of 6 meters per second. So this is v1i. This is the first object, so v1i initial is 6 meters per second, while the 2 kilogram block was just sitting here. So v2i was 0 meters per second. What happened after? After, let's say, they bounced off of each other. So the 4 kilogram box bounced off and the 2 kilogram block bounced in this direction. And we want to know what are these velocities. So this is v1 final, we don't know what this is. This is v2 final, and we also don't know what this is. So how to find these velocities? Well, Remember, this collision is elastic, meaning kinetic energy is conserved. Ki is equal to Kf for the system. Along with that, momentum is always conserved in any kinds of collision or explosion when we consider them as isolated systems. So combining these two principles, we can get to our answer. Let's do that, and let's not try and do much algebra. Ki equals Kf. What does this give me? Ki means 1/2 m initial times v initial. What are the initial masses? 4 and 2, right? So m1 times v1I plus 1/2 m2 times v2I. This is equal to 1/2 times m1 in the final situation or the final positions. For the final velocities, we have 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. All right, this is one equation, and this is for any general problem for which the collision is elastic. In addition to this, we have the older equation, that is the momentum is conserved in the collision. This means m1 v1I plus m2 v2I, taking their directions positive or negative depending on that, equal to m1 v1 final plus m2 v2 final. All right, this is equation 2. If you combine equations 1 and 2, that is, if you can separate out, sorry, I missed the squares here. Our target from solving both of these equations would be what is v1f and what is v2f, right? If you sit down and solve these two simultaneous equations, then you would end up with a very simple formula. I don't want to go over the algebra because it is just tedious algebra which will take up much of the video. So I would just give you the result. V1f, as it turns out, is m1 minus m2 over m1 plus m2 times v1I. V2 final, as it turns out, is 2 times m1 over m1 plus m2 times v1I. And this is a general result that you can use for any two masses with one mass moving at an initial velocity of v1I in any collision which is elastic. So this is not particular to this problem. This result is a very general result which you can apply to any problem. Let's go ahead and apply this result to our problem in hand. For us, when we want to find v1f, what do we have? m1 was 4 kilograms, so 4 minus m2 was 2 kilograms, it's 2, over m1 plus m2, so 4 plus 2. This is multiplied to v1I. v1I was 6 meters per second. 6 meters per second, right? And this comes out to be 2 meters per second. V2F is 2 times m1. m1 was 4 kilograms. 2 times 4 over m1 plus m2, which is 6, times v1I, which is again 6. The 6 go away, and I'm left with 4 meters per second. Look at the signs, both are positive, meaning both were moving in the positive x direction. But in my diagram, I chose the first mass to be moving in the negative x direction. It doesn't matter because I got the right answer in the end, right? So even if you draw your diagram incorrectly, it doesn't matter as long as you keep true to your diagram and keep consistent with the signs. Then you will always end up with the right answer. So in summary, when you have elastic collisions, in addition to momentum being conserved like any other collision, kinetic energy is also conserved. and we can combine those two results and find this very general set of equations that help me find the final velocity of each of the two objects involved in the collision. And this is a general result. This is not particular to this problem. All right, I hope collisions start making more sense by now.